Yeah, so I'll start with a philosophical comment that relates to the previous talk and to my talk that will follow and to what Carlos discussed in the morning. I think that astronomers often think that cold dark matter is a model that is simpler than warm dark matter or self-interacting or anything else, right? From particle physics point of view, this is philosophically absolutely wrong. You take the same model, the same particle, you take a WIMP, you make a mediator lighter, what connects it to the standard model, and it becomes self-interacting. You make a cold dark matter particle, you make it lighter, and it becomes warm. And other examples of the same kind are easy to give. So we should not search for excuses to study self-interaction or warm or other non-cold dark matter. We must do this because we don't know what dark matter is made of. Cold dark matter is not worse or better than any other. We simply should systematically study all those options. So self-interacting dark matter with quite strong self-interaction cross-section is not excluded, right? We have to study it. Warm dark matter with quite significant free streaming length is not excluded yet. We have to study it. Ruling out a model, a CDM model, or a warm dark matter, or self-interacting is very different thing. It requires much more, right? So we should not concentrate on excuses. We should objectively study what we can claim and what we cannot claim, and then try to exclude CDM or exclude its alternatives.
Okay.
I'm sorry.
No, just to say, we are going to have Alex Boyarsky that will talk about just cold dark matter is a correct alternative. I'm joking. Okay, please.
Yeah, sorry, I started a bit too early, but yeah, so my story will be devoted to sterile neutrino mainly as a dark matter candidate. And for me, it starts from what Carlos discusses, right? Why do we think that dark matter is a problem if we have a perfect dark matter candidate in the standard model, which is ordinary neutrino, massive, stable, and neutral? And as everyone knows, and as I teach students, the reason for that is very simple, because a neutrino is a fermion. So you need, you can put only one fermion in one state. And if you take a galaxy, for example, a dwarf galaxy with all astronomical uncertainties, its size is not infinite, its escape velocity is not infinite, its mass is not infinite. So you take the conservative estimates of all these numbers, you combine them, and you obtain a phase space density. And if you want to realize such a phase space configuration with a lighter particle, you need more particles, right? And at some moment, you need more particles that you can fit if those particles are fermions, because you cannot fit too many fermions in a given phase space. And this was realized as early as 1979 by these great people here. And they said, if I apply these arguments to observable galaxies, I obtain a lower bound on dark matter, fermion dark matter mass. On the other hand, from standard model, I know the number of relic neutrinos in cubic centimeter in this room. And if I multiply this number, this lower bound on the mass of the particle, on this concentration, I get simply too much, right? I get too much dark matter. So the astrophysical, the astronomical requirement on dark matter fermion and cosmological one from the early universe, they simply contradict to each other. And then, as Carlos explained me, at that time, this contradiction is not so big because the Hubble constant was not known so well and so on. So it was not a factor of 30 contradiction, but it was a factor of 2 contradiction. And that is why Carlos, with his great collaborators, tried this from different perspective and found that ordinary neutrino do not work also because they form big structures before the small ones, which contradicts to the observation, right? So this is my starting point because I want to continue considering dark matter fermion. So to do that, I need to find a solution for this problem of phase space density. And how I do that? Well, I cannot overcome the phase space density argument. It's too robust. It's very first principle argument. So what I could do, I could change the prediction of the number of these fermions in cubic centimeter in this room. And there are two basic ways to do that. One, I say that my neutrino should be very heavy, so heavy that it decouples non-relativistic, and then its number density is suppressed by Boltzmann factor. And this is what is called WIMP. And another possibility is to say that it might be light, relatively light, just above the Tryman-Gunn bound, so in keV range, but it should interact so feebly that it never comes to thermal equilibrium. It's always have sub-equilibrium number density, and therefore it's not so numerous at ordinary neutrino. And then I can afford having it lighter. Oh, sorry, heavier than the Tryman-Gunn bound. An example for that would be a particle that interacts exactly like neutrino, but with a Fermi constant that is suppressed by many orders of magnitude by certain constant that is less than 1. And then it does similar things at ordinary neutrino, but the number density naively will be also suppressed by the same number, and I will resolve the contradiction between Tryman-Gunn and Big Bang, right? How this could work? Of course, this is naturally related to one of the most simple explanation of the neutrino mass. If I have a particle that mixes with ordinary neutrino at quadratic level, like left-handed electron and right-handed electron are mixed by Dirac mass, I take right-handed neutrino. By the symmetries of the standard model is neutral, singlet, so it is not involved in any standard model gauge interactions, gauge field interactions. So it only can have mixing with the left-handed neutrino because it has Dirac mass. And it also might have its own Majorana mass, which would explain the phenomenon of neutrino flavor oscillation. This is not possible in the standard model because if we only use standard model particles, the Dirac mass would look like a higher dimensional operator with dimension-full coupling constant, which requires new physics at certain scale, the same way as dimension-full G Fermi requires W boson to exist. And to resolve this, we need to add a new particle. Many people say, okay, but why we call it beyond standard model physics? All fermions have left-handed and right-handed neutrinos, counterparts. So we did not observe right-handed neutrino because it's neutral and sterile. It does not interact, but we don't know, we cannot claim that it does not exist. Why we don't simply call it a part of the standard model? Well, it's a bit demagogical because this particle can have different mass, different interactions. And depending on that, it plays very different role in this world, right? So we don't know which sterile neutrino exists in this universe. And that is why it is unknown. So that is why it is beyond standard model physics. We have to figure out how heavy it is, how strongly it interacts. What we know is that if it exists, and if this is the explanation of neutrino mass, it should have a Majorana mass that is much larger than its Dirac mass, such that we explain the smallness of ordinary neutrino mass. It is suppressed exactly by this ratio. However, we cannot derive the value of this ratio from the value of active neutrino mass, as it is possible that you have two right-handed neutrinos and they form something similar to Dirac fermion between themselves, and then their contribution to this operator should be much smaller, that is their overall contribution to the neutrino mass, which will be much smaller than individual contribution of each of them. They kind of cancel each other. So neutrino mass is much smaller than you would expect from the masses of right-handed neutrinos and their interactions strengths. You might call it fine-tuning, you might call it symmetry, but this is not excluded. And this scenario has to be considered because we know that to explain observed pattern of active neutrino masses, you need two right-handed neutrinos because we observe two mass differences. So if we explain neutrino masses with right-handed neutrinos, we need at least two of them. And then this cancellation, because of coincidence or because of symmetry, might happen. And so we should take into account that the interaction strengths can be not as simple as this estimate shows it. The interaction strengths for a given mass can be larger. If such a particle exists, this right-handed neutrino exists, it behaves exactly as we want it, right? In any process where you can emit ordinary neutrino, there is a probability to emit also a right-handed neutrino because of this quadratic mixing. Ordinary neutrino oscillates into sterile one, and it can be in this way created or it can be destroyed. Then its behavior would be exactly like for ordinary neutrino, only with Fermi constant multiplied by some small number. So what would happen in this case? Naively, you say normal neutrino have concentration when they're relativistic that goes as temperature cubed. Their cross section goes as energy squared, so temperature squared. So you have this famous T to the 5 reaction rate. So the number of such reaction, the number of such reactions per second would behave like temperature to the 5. And to check whether they are in thermal equilibrium or not, we have to compare it with Hubble expansion rate, which behaves as T squared. And T to the 5 will always win over T squared if the temperature is large enough. So it does not work, right? At high enough temperature, our particle will be in thermal equilibrium. Reaction rate will be larger than expansion rate of the universe. And so it's not what we wanted. It will be another kind of thermal relic. No, it's not true. And it is not true because all this happens in plasma. So in plasma, neutrinos interact with other fermions through weak interactions. So the properties of ordinary neutrinos are changed. This diagram has to be dressed with all processes, all interactions with the background plasma. And as the result, we get mixing angle, this small constant that is suppressing Fermi interaction, depending on the temperature. And this temperature, this dependence is very non-trivial. So as a result, the mixing angle, and correspondingly, the ratio between reaction rate and Hubble rate changes with the temperature, and it changes as a power law and very fast. And maximal reaction rate as compared to Hubble rate happens at certain temperature. It peaks. So you can think that these right-handed neutrinos would be mostly produced in the early universe around this temperature. Where is my around this temperature here, right? So and then two possibilities are we can imagine two possibilities depending on the vacuum value of this coupling constant of the mixing angle. This whole curve can go up and be above 1, which means that our particles come to equilibrium at certain high temperature, they stay in the equilibrium for some time and they go out of equilibrium. And if the vacuum value of the mixing angle is smaller, all this curve goes down and it might never reach 1. And then we have our super WIMP scenario when the particle is never in thermal equilibrium. And this is what we wanted, because then its number density will be suppressed. So this would be the thermal relic, and this would be a super WIMP, which is never in thermal equilibrium. If you look at numbers, you can say that 2 right-handed neutrinos that we need to explain neutrino masses, they cannot live here. These mixing angles would be too small for that. So particles that explain neutrino masses, 2 particles, 2 right-handed neutrinos, would live here and they would decay quite early in the early universe. They would not contribute to dark matter. So if you want to explain neutrino masses and dark matter in this way, we need at least 3 right-handed neutrinos. 2 of them live like this and 1 lives like that. And then the smaller one, the one that has a very small interaction constant, could play the role of dark matter. It would have naively the phase space distribution like ordinary neutrinos, thermal, but suppressed by a small number, and never reach thermal equilibrium, so it would overcome the Tryman-Gunn problem. And also, with such a small coupling constant, it should not be necessarily stable. It might decay, and moreover have a radiative decay channel, and still have lifetime larger than lifetime of the universe and be a good dark matter candidate. So naively, to test this model, sterile neutrino dark matter, we need to forget about 2 other particles and say that we will simply search for signatures of warm dark matter and decaying dark matter. Partially, it's true. It's definitely something that has to be done. But we have to keep in mind that we have only one universe, right? And different processes that happened in different stages of the universe evolution might affect each other. And if we want to not just constrain warm dark matter and decaying dark matter, but we want to use it to apply to a concrete particle physics model, we need what Tom Tunes calls holistic approach. We need to look at the whole history of the universe. And I'm going to give you an example of that. 2 heavy sterile neutrinos that can, time is going so fast. 2 heavy sterile neutrinos that can explain neutrino masses. They also are known to be able to explain baryon asymmetry of the universe because of CP violation in their mass matrix and so on. And so with 3 right-handed neutrinos with the masses below electroweak scale, we can explain all 3 beyond standard model problems: baryon asymmetry, dark matter, and neutrino masses. And these heavier particles can be searched and are actively, very actively searched at the accelerators. They are searched at colliders, at LHC, FCC, especially FCC EE, would make even better job searching for them. However, decay length, the distance this particle travel before they decay, gets parametrically much larger when mass gets smaller. So if your mass is below 10 GeV, particles can fly so long distance before they decay that they simply cannot be found at any colliders. You need a special type of experiments to search for them and close this window, which will never be closed with colliders. And this is now being very seriously considered in CERN, and we will know the decision in several months whether this experiment goes ahead or not. And you could say again, but why we should care about that from dark matter point of view? And let us see what happens in the early universe is these three particles exist, right? And I emphasize again that we need three particles to explain at least neutrino masses and dark matter. So at some high temperature, heavier right-handed neutrinos were not in thermal equilibrium yet, right? And they could satisfy Sakharov conditions and generate baryon asymmetry via lepton asymmetry. So a very large lepton asymmetry is generated at high temperature. Then these particles go into thermal equilibrium. However, they could trigger generation of magnetic fields, something like dynamo, because they break left-right symmetry, cause dynamo-like instability in Maxwell equation, and plasma becomes very turbulent and full of magnetic fields. And this magnetic field carry information about lepton asymmetry. And when two right-handed neutrinos go out of equilibrium, this lepton asymmetry is again released, and plasma becomes particle-antiparticle asymmetric in the epoch when dark matter is produced. Again, why would you care? The answer is because this significantly affects production of dark matter, sterile neutrino. In the presence of a large lepton asymmetry, it becomes resonant. So only particles, only neutrinos with certain momentum produce right-handed neutrinos, produce dark matter particles efficiently. And then the spectrum becomes very different from a thermal spectrum. So for the same mass, your average momentum becomes significantly smaller, and it depends on the lepton asymmetry. So if you want to constrain this model, you should take this into account. Lepton asymmetry becomes a parameter for cosmology then. But moreover, magnetic fields that were produced during all this, they make plasma more inhomogeneous, and they generate additional matter power spectrum at the scale of dwarf galaxies. And people did simulations about that, and the properties of the Milky Way halo and its satellites that we observe might change in the presence of such magnetic field. And this is something that should be taken into account if you want to constrain not just warm dark matter, but to translate it into constraints on particle physics model, which is sterile neutrino. From this point, I was supposed to start a new talk describing how to constrain warm dark matter. As Paolo tells me, I have no time for that. So the only thing I want to say here is that first, if we want to, again, if we want to apply decaying or warm dark matter constraints to particular particle physics model, we should completely change philosophy. We should stop being model independent and start to be very model dependent and put everything in holistic picture of the universe, assuming this particle physics model. This is the only way to produce correct constraints. And second statement I want to make from the part of the talk that I didn't make is that I absolutely agree with Carlos that we are now at the moment where it is possible to make a conclusive test of CDM or non-CDM. And I believe that strong gravitational lensing, gaps in stellar streams, and Lyman alpha forest, each of these methods have data that are in principle sensitive to the required scales. The main problem on that side is to interpret properly this data, because in every case, we have other effects that can be easily confused with the effect of dark matter. And this cannot be treated as systematics because these effects are of the same order, the same size. So to do that, we have to learn how to distinguish between these two effects rather than putting formal statistical constraints. And then to apply it for particle physics to say that mass of sterile neutrino is smaller or bigger than that, a lot of extra work is needed because you need to embed these model-independent robust constraints into the holistic universe within your particle physics model. Thanks a lot.